Hi, this is Mrs. Gibb. We are going to move on now. In the last video we covered entropy, and we used the delta S is equal to the sum of the entropy of the products minus the sum of the entropy of the reactants. And then I talked a little bit about how positive entropy means the reaction is more favorable because positive entropy means it's getting more and more disorderly. So a positive thing is a good thing. And we've also talked about negative heats. Change in heat is a good thing. So we have to look at both the entropy over here and the heat over here. So this is an exothermic reaction and an increasing in entropy. So both of these would be favorable conditions. And this is exothermic and decreasing in entropy. So this would be favorable and this would be unfavorable. This is endothermic and increasing entropy. So this would be the unfavorable part and this would be a favorable part. And this is endothermic, which is unfavorable, and decrease in entropy, which is also unfavorable. All these things combine. And we need to be able to figure out how to use them to know whether a reaction will actually be spontaneous. So Willard Gibbs formulated a single way. He combined entropy and enthalpy. Remember, enthalpy is the H, into something called free energy, or Gibbs free energy, and that's a G. It's one of those times when the variable makes sense. So here's the formula. Delta G equals delta H for the enthalpy minus T. And here the T is kelvins. Before we've been using, and in the Q equals MC delta T, this little t is for degrees Celsius. Capital T's are usually meant for kelvins. So a capital T, we use kelvins. And I haven't been consistent about that, but a small t, we use degrees Celsius. So in this formula particularly, though, you need to make sure you use kelvins. So delta G is a change in free energy. A negative delta G, this is important, indicates a decline in free energy and signifies that a reaction may occur spontaneously, okay? So this is kind of a way of figuring out if the reaction is going to happen. So now what we're going to do is we're going to calculate the delta G. So what we've said in the past is a negative delta H is exothermic, and that's a good thing. And a positive delta S is an increase in entropy, and that's good. And well, now we're telling a negative delta G is good. That's how we know if something's going to occur spontaneously. So see that negative G, is it spontaneous? A positive value is not spontaneous. So two ways to calculate a delta G: products minus reactants, just like before. I don't know why I have the S here, but that should be a G. The delta G and a G of the products minus the G of the reactants. I think I just meant to change that and I forgot. So change that in your notes. We're talking about Gibbs free energy now, or we can use this formula. Okay? So we're going to calculate Gibbs free energy for the following reaction. And so we're going to try to do it both ways. Now we're going to be using this chart. Let's see, do I have it pulled up? Yeah. This big old chart. That's a copy from your textbook. Notice how it has the delta H formations, the entropy values, and the delta G values. So we'll be kind of referring back and forth to this. So here I went ahead and wrote the formula. Now notice it gives us a temperature, and that's kind of a clue that use the one that gives you, that has temperature included. So I'm going to go, the first thing you need to do is look up the delta H of formation for each one of these things, and the delta S, which is the entropy, using the chart. So we have silver. Now silver is an element, so all elements, their formations are 0. So silver and sulfur, the delta H of formation is 0. We have to look up Ag2S solid, find the delta H of formation for that. So Ag2S solid, the delta H of formation is negative 32.6 kilojoules per mole. So we'll write that in there. Negative 32.6 kilojoules per mole. And now we have to look up the entropy values for silver solid and sulfur solid. So go back and look at that thing again. Silver solid entropy is 42.6 joules per mole times Kelvin. So the units changed a little bit. Notice that. It's joules per mole times Kelvin. So for silver it is 42.6 joules per mole times Kelvin. And for sulfur solid, and I'm doing this just so you can see how I'm using it. There's the sulfur, there's the formation. The next one is the S, so it's 32.1. 32.1 joules per mole Kelvin. And then for Ag2S, we got to look that one up. Ag2S, there it is, and it's 144.0. joules per mole Kelvin. All right, so that's the value. So you need two sets of values. So to calculate delta G, we're going to first need the heat of formation, the change in the heat of formation, which is products minus reactants. So we have to calculate that. The delta H of formation is the sum of the H of the products minus the sum of the H of the reactants. Well, in this case, remember that this side, this is the reactant side, and this is the product side. Well, we have zeros right here for the reactant side, so we will be subtracting 0. And then the products, we have 1 mole of it, and remember we have to be careful about that. 1 mole of it, so 1 mole times a negative 32.6. I'm going to give myself a little more space right here. So negative 32.6 kilojoules per mole. So the moles cancel, and it's just a negative 32.6 kilojoules. So that is my delta. That's the first thing I put in. So negative 32.6 kilojoules. Okay? All right, now I need to calculate, let's see, well, I don't have to calculate the T. I just write down the negative, and the T is already given to us, 298 kelvins. And I need to calculate the delta S. Well, delta S is the sum of the S of the products minus the sum of the S of the reactants. So this one's going to be a little longer because we have values for each one of the things. So first we do the product side. We have 1 mole. So 1 mole times the S of the products. Remember the product side. So times, I'm going to make these brackets, 144.0 joules per mole times Kelvin. And that's all there is on the product. So it's not a sum. There's nothing else to add to it. Subtract out the sum of the reactants. And we have this one. We have 2 moles of it. We have to use that 2 in front. So 2 moles times 42.6 joules per mole times Kelvin, plus 1 mole times 32.1 joules per mole times Kelvin. And that's the second side. Okay? So it's the sum of the products minus the sum of the reactants. So we need to add the reactants up first. Let's cross out our units. We got rid of the moles. So we just have joules over kelvins. And then we have to say 2 times 42.6 plus 32.1. And so I'm going to pull those, put those numbers in. All right, I put the values in. I crossed out the moles here. And so I brought this down over here. There's the product side. And then I added the 2 reactants, and I put it right there. So that's the reactant side. I subtract the 2, I get 26.7 joules per Kelvin. Okay, now there is a problem. This is kilojoules on this side, and this is joules. So we need to convert this to kilojoules so that we have the same units, because we can't add or subtract them if they're not the same unit. So 26.7 joules. There are 1,000 joules in a kilojoule. And so we're just going to divide 26.7 by 1,000 to get 0.0267 kilojoules per Kelvin. So now that's what the new value is, 0.026. So we put this over here. 0.0267 kilojoules per Kelvin. All right, now we got to leave that per Kelvin in there because that's important. Now we can cancel some things. So let me use another color. Kelvins and kelvins cancel so that we have just kilojoules. So we now take a negative 32.6 minus the 298 times 0.0267. All right, when I do that, I get negative 40.5566, and we need to adjust for sig figs. And so we can use everything. This is a measured value. It has 3 sig figs. This has 3 sig figs. This has all has 3 sig figs. So 1, 2, 3. So it's negative 40.6 kilojoules. That's the unit, negative 40.6 kilojoules. So delta G is negative 40.6 kilojoules. So this has a negative delta G, so this is a spontaneous reaction because it has a negative delta G. Okay, make sure you have that filled into your notes, and we're going to do the next one. Okay, if you need to pause it and do it, go it right here. All right, now I'm going to go ahead and do this one for us. We're going to calculate it again. Now this is in this case, what we had was a negative delta H, and we also had a positive, right here, a positive delta S. And that was the first situation, a negative delta H and a positive delta S. So we're doing a problem for each one of these. All right, now let's go down. We're going to fill in this one the same way, calculate the Gibbs free energy using the same formula. I suddenly forgot what it was. Delta H sub F minus T times delta S. The T is still the same temperature, 298. So I'm going to have to calculate the delta H, and the delta S. So I'm going to go look up the values. I'm not going to go back and forth and show you. You just got to go back to that same chart, that big chart, and find them. And I'm going to list them out here. All right, I went and found them on that chart. Right here, I found them all on that chart, Fe2O3 and a lot of different ones, and filled out the H values and the S values, and now we're going to calculate the G. So for the delta G, we're going to need the delta H first. So I'm going to do that. I'm going to calculate it over here. The heat of the products minus the heat of the reactants. In the products, it's going to be a negative 824.2 kilojoules per mole, and there's 1 mole, so I forgot to write that in there. And then the heat of the reactants, it's all 0, so C 0 and 0. Okay, so again, it's just going to be, this time we have delta H is a positive, sorry, no, it's negative, still negative, so it's products minus, right, negative 824.2 kilojoules. Okay, now that I have that, I just got to calculate the delta S, which is the S, the sum of the S of the products minus the sum of the S of the reactants. So products, this time we have 1 mole, and that's the formation. There's the delta S. So it's times 87.4 joules per mole Kelvin, and that's the only product. So minus the reactants, the summation of the reactants. We have 2 moles of iron, and we have to use 27.3 joules per mole Kelvin. And we have 3 halves a mole, and the only reason they did that is so they'd have 1 mole over here to show you the heat of formation. So we have to add 3 halves of a mole of oxygen times 205.2 joules per mole Kelvin. All right, I'm going to have to do the math to add these together, and then I'm going to do that and put it on here for us. All right, I went ahead and did it, and I multiplied these two and multiplied these two and added them together and got this number and subtract it, and I still have a negative 275 joules, so the delta S is negative. So now we're going to put this back in. The heat of formation was a negative value, negative 824.2 kilojoules. And the temperature, oh sorry, I got to subtract it. I'm not multiplying it right there. Erase that. Minus the temperature is 298 kelvins, and multiply that by a negative 275 joules per Kelvin. All right, now, again, we have this joules issue that we need to turn the joules into kilojoules. So negative 275 joules, we got to turn it into kilojoules. So it's negative 0.275 kilojoules. So 0.275 kilojoules, okay? Now we can multiply these, and so you'll notice that the delta S is negative here. Multiply everything and get the final value for this. All right, when I get to the final value, delta G is negative again. So it's still spontaneous, even though the delta S was now negative, which is not normally spontaneous. Okay, so we combine the two, and it's kind of a ratio of the two depending on the temperature. The temperature has a lot to do with it. All right, I hope you got that one down. If you need to, stop the video and write all that in. And I'm going to go ahead and do this one for you. And this one is going to be the third case, and see what we get here. Okay, I apologize. This one needed to have C2H4, and I wrote C2H2 by accident. Okay, so put C2H4 there. No, C2H2 is right. I'm sorry, I'm looking at the wrong problem. All right, I corrected it. I was right the first time, but I didn't. I was looking at the wrong problem for this. So it is C2H2, and so we calculated the delta S. I went ahead and the delta H formation is just whatever it is, because these are zeros. Products minus reactants. These are just zeros. So we have 1 mole of the product times its entropy right here, and we have to subtract 2 moles of the reactant times its entropy value, and 1 mole of the hydrogen reactant times its entropy value. And we end up getting 58.8. So delta S is positive, and that's a spontaneous situation. That's a good thing. So now we're going to calculate delta G, which is delta H minus T delta S. All right, so the H this time is 227.4, so it's a positive value. The temperature is still 298 kelvins, and we have to convert this in again. So this is going to be 0.0588 kilojoules per Kelvin, because you just divide by 1,000, 1, 2, 3. So 0.0588 kilojoules per Kelvin. And now we can cancel out the kelvins, so that our delta G value is 209.9 kilojoules. 209.9 kilojoules. So delta G now is positive. This is not spontaneous. We had a good entropy, but not a good enthalpy, because enthalpy should be negative and entropy should be positive. All right, we have one more situation. Again, make sure you have this written in, make sure it's correct, and then we'll go on to the next one. There's a lot of these, I know. All right, I'm not going to go through the process of calculating the delta H this time, or the delta S. I just looked them. Basically I looked in the book and got the answer, because it's the exact same process. Products minus reactants. In this case, we have something that's not normally good for delta H, so that's not normally good. And delta S is also not normally good, because it's negative, and delta S should be positive if it's going to be spontaneous, and delta H should be negative if it's going to be spontaneous. So we put them in to this delta G situation and see what happens. So we have the kilojoules here minus the temperature of 298 kelvins times, all right, we have to convert this 1, 2, 3 again, so times a negative, let's write that, negative 0.0535 kilojoules per Kelvin. Ignore that little dot right there. Back to the pen, there we go. Alright, so cancel out your kelvins and then add these all together, and the value we get for this situation is a negative 53.5 kilojoules. So delta G is a negative 53. So up here it was a positive, and that's not spontaneous, but here it's negative and it is spontaneous. So even though these two situations were not spontaneous, we have a temperature that makes it spontaneous. It's that we end up subtracting such a small amount. Well, we end up subtracting enough that we end up making it spontaneous. Okay, I misread again. That's what I get for just trying to copy something down rather than working it myself. Okay, because I was thinking that does not make sense when I was talking about it. So let's correctly do this. Okay, 52.4 kilojoules minus, let's multiply those two guys together and get a number. I'm going to just go ahead and do it the old-fashioned way and not try to cheat. I know what I'm doing, but I'm trying to get the video finished. So 298 times a negative 0.0535. I was about to say that's just a small number. Whoops, I must have put that in incorrectly. Try that again. 298 times a negative 0.535. No, 0.05. Okay, really, I'm having a bad day. 0.0535. All right, negative 15. I think that makes more sense. So subtract negative 15.943, negative 15.943, and now that's in kilojoules. So when you subtract a negative, you add a positive, so the value should actually have gone up. So 52.4, subtract a negative, I'm just going to do it the whole way, subtract a negative 15.943, and I get, there we go, 68.3. 68.3 kilojoules. Okay, so delta G is positive. This is also not spontaneous. That makes way more sense. Okay, that's what I get for trying to just look at it and not work it out. Work it out. And this is and when I look at it, I find the right answer, and I was just looking in the wrong spot. So this is also not spontaneous. Now, these math problems are tedious, but they're not hard. And so they'll take a lot of time, but just because you got to get all your values, but they're not hard. Okay, now we're going to do at least one more example problem together. And I'm going to work it out. Determine whether this reaction between ammonia and hydrogen chloride is probable at 298 kelvins and at 1,000. So basically want to know, looking at these two temperatures, okay, at these two temperatures, which one is going to work, okay? That's what we're trying to figure out. Is it probable? So we're going to calculate the delta G. And so first I'm going to go and look up all the values. I'm going to go ahead and do that for you. I'm going to look up all the values and come back and put them on there. Okay, first I want you to see I looked up all the delta H's and delta S's. And so I'm going to go ahead and calculate delta H, which is the sum of the H of the products minus the sum of the H of the reactants. And then I'll write, and you can stop. All right, so I went ahead and did it, and excuse me, all the moles cancel. So the delta H for this is negative, which is normally good, and the delta S is also negative, which is normally bad. So we're going to put both of those in to calculate delta G, and we're going to calculate it at 298. So we start off with negative 176.2 kilojoules, because it's the delta G equals delta H minus T delta S. So first the delta H value, this is the delta H, minus the first temperature is 298 kelvins, and the delta S value is a negative 0.2851 kilojoules per Kelvin. All right, so go ahead and cancel kelvins and calculate what this first delta G is. This is for the 298 temperature. And we'll figure out if that one's probable. All right, so for the first one, I get that the delta G is a negative 91.3, which that makes this probable or spontaneous. Now we're going to do the same thing, but with 1,000 degrees Kelvin, or 1,000 kelvins, and try to see if that one would be probable. So I'm going to put this off to the side. This is for the 1,000. All right, now the values for delta H and delta L, these were for the standard state, which is the 25 degrees Celsius or 298 kelvins. So that's the things that we have on the chart. Now we're going to calculate the delta G using the same values, even though they're not at standard state, because it's a good estimate, and that's what I did here. It's a good estimate, and when I do that, I can see that the delta G is positive, so this is not a probable reaction. So even though we don't know the exact values for the delta H's, the formation and the entropy, because we only know them for 298 standard state, I can estimate what they would be. I can estimate what delta G would be by using them. And it still gives me a good idea that this would not be a spontaneous reaction. Okay, so that's the end of the honors notes, and you're going to be determining these kinds of questions. The only kind of question that we really haven't covered is if I asked you what temperature would something have to be in order for it to be spontaneous. You might have to figure that out based on, you want something where the delta G would be negative. And so you got to calculate a temperature when the delta G is negative. And I may go over one of those in a different video. But that's all there is for now. So I hope you got that.